The final topic in section 8, partial differentiation, is actually total differentiation, where we're going to define the total differential and understand how we can use it for and why it's so useful in physics, for example. Before we do that, let's introduce the concept behind it. And if we think back to functions of just one variable, if we look at the ratio between the small change in x and the corresponding small change in y, this would be approximately equal to the derivative at the function at a specific point. What this also means is that therefore we can look at the change of the function, this small delta y, essentially by multiplying the derivative of the function at the point times whatever delta x we're applying to the function. This, in a way, gives you the total change of the function because the function only depends on one variable. Now that we've been dealing with functions that depend on x and y, can we find a similar concept? Can we find the total change? In other words, dz, for example, if this is function z, the total change of function f. Before we do that, let's get rid of the case of just one dimension and go step by step towards understanding how we can do this and also how we can extend it to functions that might also depend on z or even more variables. Let's consider a function g that depends on x and y. First of all, let's keep y fixed and look essentially at the change that we can write dg when x is changing. And we can write it in the same way as we did for functions that depended on just one variable. We can write that this is approximately equal, but in this case to the partial derivative of g in respect to x multiplied by how much we're looking at. What is the change in x that leads to a corresponding change in g? Let's call this delta g1. The other case is when x is fixed. And in this case, we can have a look at delta g2. And in a similar logic, we would calculate this by looking at the partial derivative of g in respect to y, and we multiply this by the change in y. Remember, x and y are variables and they can change. In order to obtain the total differential, or the process that we'll call total differentiation, all we have to do is essentially sum this. We'll say that the total change in g is going to be approximately equal to the change when we fix y and the change when we fix x. In other words, this is approximately equal to the partial derivative of g in respect to x times the change in x plus the partial derivative of g in respect to y times the change in y. And this is what we call total differentiation. What is this useful for? Well, it is useful for you to estimate the total change of a function that depends on more than one variable. And we'll see some examples, and you have even more in your lecture notes. This can be useful whenever you have a function that depends on various parameters, and they're all changing in different ways, but you still want to see what is the final change, or maybe you want to see what is the combined rate of change if all of these are changing with time. In order to do this, let's think of a practical example. Let's say that you have some volume, and this volume is a function of, for example, radius and height. Now, let's say that for some reason you want to calculate what is the total change of the volume when both r and h are varying. This means you know that delta r will be some value You can even call it A, and the height will be varying by an amount B. How do you know the full variation of the volume? For this, you use total differentiation. What you do is you calculate the partial derivative of V in respect to R, and you multiply, and I'll leave it like this for now, but you could sub it in later on. You multiply by the change in R plus the partial derivative of, in this case, the volume in respect to height times the corresponding variation in height. In this case, because we would know that this is A and B, but this is still for a generic function, so we can still keep, for example, VR, if we use the notation that we've defined and that we've been using so far, times A plus, in this case, this is the partial derivative V in respect to H times B, which is delta H. Total differentiation really allows you to estimate what is the total change of a quantity that depends on other quantities. And it's all about calculating the partial derivatives and then multiplying by the corresponding change. Another really cool application, let's keep it in terms of volume, but it could be anything really. Let's say that you want to know how some volume is changing with time. So you want to look at the derivative of V in respect to time. How do you do that? Now, provided that as ingredients, you are told, in this case, what is the variation of R in respect to T, and the variation of H in respect to T. In other words, the rates of change in terms of time. You can calculate the total change of the volume in respect to time by a very similar process. You look at the partial derivatives, in this case volume in respect to radius, and instead of multiplying by the R, in this case, because you're looking at rates of change, you're multiplying by the rate of change of R in respect to time, and then you do the same for the height, and you multiply by the change of height in respect to time. This is another very nice example of using total differentiation, but now to estimate the rates of change. And you'll see that comparing this version with this, that if you look in terms of Leibniz notation, you will see that it's fully consistent throughout. In this case, I've actually written equals to, because these things are things you can calculate directly, and they're not just increases, they're quantities which will tell you, for example, what is the increase of the height per second, for example, meter per second, and in this case also meters per second. And then in terms of volume, you'd be looking at a change in terms of cubic meters per second. And the other units would be encoded when you look at dV over dr and dV over dh, which will have units of meter squared. Multiply by meters per second, you get meter cubed per second. The other application that total differentiation has is, for example, to estimate errors. And specifically, in keeping to this example, if you have some volume that you want to estimate, and in the lab what you're actually measuring is some radius and some height, then you can estimate essentially the error in the volume. You can approximate it, this is one way, essentially by looking at the sum modulus of dV dr times the error in your measurement of the radius plus the modulus of the partial derivative of V in respect to H times the error in H. So this is a very nice way to look at errors, even though probably The most common way of combining errors is to use them in quadrature, which for the sake of completeness, let's just put it on the board. And that in general for errors in the lab, you'd probably be looking at estimating your error in V in the lab more like the square root of the sum of these partials, so that you do the partial derivative in respect to r in this case times the error, and you'd even write it like this. This is your experimental error in measuring a parameter, and then you square it plus, and then you calculate the partial derivative of v in respect to h times your error in height, you square it. So this is typically a more general way of estimating it, but you can also estimate it directly. This is probably a more conservative way of doing it than this. That assumes that errors are actually not correlated. If they are correlated, then doing this is even better. But perhaps the most important point is to understand that partial derivatives will have numerous applications. Not only to estimate how a function is varying along a specific direction, to find stationary points, to find the total change of a function, or even to combine errors in either quadrature or just by summing the modulus. Finally, before we conclude section 8, I would definitely recommend you to try all the problems and examples that are available in the lecture notes, not only for total differentiation, but also in terms of finding stationary points and classifying them. Get in touch if you have questions. And once you're done, you're definitely ready to move into section 9. Since my work here is done for section 8, it's probably a good time to use the magical ukulele and disappear for a while. So I'll see you in the next video and section where we'll be discussing coordinate systems, first in 2 dimensions, then in 3 dimensions, how we can convert between them and some useful application. So I'll see you in section 9.